Okay, so FRQ number 4. This one is talking about a nonlinear spring. And then for part A, it asks us which quantities should be graphed in order to yield a straight line whose slope could be used to calculate a numerical value for A. So right here, they give us the formula, which is F equals AX squared. So to produce a straight line, I would just use F and then X squared. So because if you just use X, it would produce a line that is not linear. So the two quantities that you would use would be F and X squared. So F and X squared are going to be basically your values for the graph that you're going to be graphing later. So for part B, it asks us to calculate the values for which the quantities identified in part A that are not given in the data and record these values in the table above, label at the top of the column, including units, copy chart on paper if you need to. So they leave us this chart extra right here. So what I said was we needed X squared, right? So X squared, and then that's going to be in meters squared. That's units. So basically all we do is we just square these values of X right here. So just write these in. Okay, done with part B. Part C, it asks us to use the grid below or generate your own plot the quantities you indicate in A, label the axis with the variables and appropriate numbers to indicate the scale. So I basically just did this before recording the video just to save us some time. Our x-axis is our x squared, which is in meters squared, and then our y-axis is our force, which is in newtons. The intervals for the y-axis are going to be in 20, and then our intervals for the x-axis is going to be in 0.01. So what I'm going to do now, I'm just going to graph it. Okay. This is going to be 4. 17. 38. On here. 68 will be around here. And then 106 around here somewhere. Okay. I'm just gonna use my ruler. That. Let's fix this up here. Okay, that's part C. And then for part D, it asks us to use a graph to calculate A. So D, it asks us, so we know that A is a slope. So we know that slope is rise over run. So what we're going to do is rise. So our values for our numerator, we're going to use our force values, and our values for our denominator, we're going to use our x squared values right here. Now I'm going to pick 2 points that are on my line of best fit right here, and that's going to be 0.0625 and then 106, and then this is going to be 0, 0. Those are going to be my 2 points I'm going to use. So on our line of best fit, it's going to be 106 newtons minus 0 newtons over 0.0625 meters squared minus 0 meters squared. And then that's going to leave us with a value of 1696. And then that's just going to be our constant. That's our value of A. For part E, it asks us to calculate the work done by the cart in compressing the spring 0.1 meters when it's from its equilibrium length. So basically, it's there's a spring attached to a wall, and then a cart hits it, and then it compresses a certain amount. So we're asking how much work is done by the cart. So part E, you can't see that here. Part E. So we know that f of x equals ax squared, right? We also know that when we integrate force with respect to x, we get work. So 0 meters, and then it compressed 0.1 meters, right? We integrate f with respect to x, leaving us with 0, 0.1. Don't need to label anymore. We know our a constant is 1696, and then x squared, like that, dx. So what we do now is we basically just punch that into the calculator. If you want, we can just integrate by hand. And that's going to give us work equals to 0.565 joules. Now part F asks us to calculate the speed of the cart just before it strikes the spring. So we know that work equals change in KE, right? So now the V final of the cart is going to be 0 because we know the cart is stopping. It's going to be stopped by the spring, right? So we're looking for our V initial, the speed of the car when it hit the spring, right? So we're gonna use the work we found earlier, but this time it's negative. It's because a negative value of work, because the spring acts against the cart. So the spring is doing work against the cart, which is a negative value. So negative 1/2 mvi squared. Take out the negatives. So that leaves us with, when we move it over, 0.565 times 2 divided by our mass, which is going to be 0.5 kilograms. I'm just going to include the units, joules, right here. That. And then we put that in a radical. That's going to give us our VI, which is the speed that the car hit the spring at. And then that's going to give us, when you punch in the calculator, 1.504 meters per second. Thank you.